Belongs to Dr. NGP Institute of Technology. I am working as a professor in biomedical department. I am handling principles of digital signal processing for third year biomedical engineering students. In a new teaching learning method, today's activity is flip-flop class. Flip-flop classroom is an instructional strategy that reverses the traditional learning environment. In this activity, students have been already separated into different groups and given topics in Butterworth filter. Now the students will continue.
Good morning. Myself and my friends are coming from Dr. NGP Institute of Technology. We specialize in biomedical engineering. Today we are going to discuss about Butterworth and the history of Butterworth filter. Butterworth filter was formed by Dr. Stephen Butterworth. He is a British physicist and an engineer. He was born in 11th August 1895. His father is Mr. Alexander Butterworth and his mother is Mrs. Elizabeth Butterworth. His father is a postman. So Butterworth filter generally is a class of electrical signals which are used to separate different frequencies of electrical circuits. So,
in 1939, he was working as a principal scientific officer in the Admiralty Research Laboratory at the Admiralty's Scientific Research Center. He determined the electromagnetic field around submarine coils carrying alternating current. In 1942, he was awarded the Order of the British Empire. He was a first-rate mathematician, and he retired from Admiralty Research Center in 1945.
The Admiralty Research Laboratory is a UK-based laboratory. Here he worked on both simple and difficult equations. He worked on a basic equation and he published a paper called On the Theory of Filter Amplifiers. For this he used RV valve amplifiers. In this he explained about Butterworth the waveform. This article was published in a magazine named Wireless Engineer and Experimental Wireless and Wireless Engineer. In this note, he stated as apart from the compactness, the system in an orthodox system, it produces a uniform sensitivity in the pass region.
He mostly used even poles in his filter. He mostly dealt with even poles. His higher order filters they were separated by two pole filters and two pole filters separated by a tube amplifier. The coil forms were of dimensions, the diameter were of 1.25 inch and the length was about 3 inch.
Many scientists had worked on the frequency responses, but everything had in-band ripples. So Butterworth tried to bring flat ripples, and he was the first one to introduce frequency response with flat in-band.
The main thing for the flat frequency response is that whatever needed input, the output will be the same as the input. Whatever comes in, it goes out. So we are using flat frequency response, and the main need for using flat frequency response is that we don't get any distortion or any noise in that, so that we can get the accurate results. Thank you.
Butterworth filter. The magnitude function is given by h of j omega is equal to 1 divided by 1 plus omega by omega c. The whole power 2n and the whole power 1 by 2. Here omega c is the cutoff frequency and n is the order of the filter. First, the three conditions are assumed here. If omega is less than omega c, then the magnitude function is approximately equal to 1. And if omega is greater than omega c, then magnitude function decreases rapidly. And if omega is equal to omega c, the curve passes through 1 by 2, that is 0.707, corresponding to -3 decibel.
In the first equation we get h of j omega modulus the whole square equals 1 divided by 1 plus omega to the power 2n, where n ranges from 1 to 13, where omega c is taken as 1. Here we substitute omega equals s by j, and thereby it comes as omega j square, that comes as h of omega the whole square. If I substitute s by j, it comes as minus s square. I split it into 2 and hence it comes like h of s into h of minus s. So I bring the above equation by replacing s by j, and therefore I get 1 divided by 1 plus s by j to the power 2n. I split 1 by j as minus 1 to the power n, and the equation is 1 divided by 1 plus minus s the whole square, the whole power plus n.
Conditions are assumed here. One is even and another one is odd. For odd condition, we are equating the denominator is equal to 0, so that we get s n is equal to e power j 2 pi k divided by n. For even condition, that equation is reduced, that is k is reduced to 2k minus 1 divided by 2n. K ranges from 1 to 2n.
n equal to 1 in the equation, sk equal to e power j by k by n. We know that k equal to 1 to till 2 power 2n. 2n in here n equal to 1, so k is equal to 1 and 2 only. Substituting n equal to k equal to 1 and 2 in the equations, we get minus 1 and 1. For the stability reasons, we consider only the left hand, that is minus negative. So s equal to minus 1, so s plus 1 equal to 0. For n equal to 1, s plus 1 is the
We take n is equal to 2. Since n is even, the formula is sk is equal to e power I 2k minus 1 by 2a. And substituting the k values, we get the following poles. We have to take only the left half of the poles. So we take the negative 2 poles, and substituting the equation, we get s plus, using a plus b and a minus b formula, we get the following quadratic equation. And this is the denominator for second order.
For n is equal to b, we get a value as 6, and so we get 6 poles from s1 to s6, and we get the poles, we take the negative poles because it lies on the left hand side, and so we get this quadratic equation as h of s is equal to s plus 1 s square plus s plus 1 equal to 4. Since n is even, the formula will be sk is equal to e power j 2k minus 1 divided by 2n, where k ranges from 1 to 3, 4. And here k value, we get 4 into 8 is 8 poles, and we take only left hand side of the s plane. So we get h of s is equal to s square plus 0.84 s plus 1 into s square plus 0.76 s plus 1.
Applications of Butterworth filter, and I am going to tell you about the application of Butterworth filter in radar target tracker. Due to the noise, when the track is being collected, the data will get cluttered in the display. So a round transformation method is done to reduce the noise, and this is done using designing a Butterworth filter digitally. For the specifications and parameters, the spectral characteristics should be analyzed and then designed. Finally, the noise is being magnified by the transformation method, and the signal is smoothened. This can be done using MATLAB, and this is the application of Butterworth filter in radar design.
Signal processing is used to manipulate, enhance, filter signals such as speech, audio, image, and telecommunications. Some noise may be in their signals, so filters are used to remove noise. Two types of filters are used: tunable filter and fixed filter. Fixed filters remove noise within the passband and stopband frequencies, whereas tunable filters uses fixed and stopband frequencies can be varied. The tunable filters are used in medical electronics, telecommunication, and control systems.
I'm going to share something about the real-time applications of digital low-pass Butterworth filter in the differential data processing. Let us consider a pneumatic cylinder. The pistol displacement of pneumatic cylinder is measured by using a displacement sensor, and then the speed and acceleration of the pistol is measured by using a differential amplification on the displacement time curve. If we process this curve, the error is very larger and the curve moves forward overall. So we are going to interface the curve with a digital low-pass Butterworth filter. If we interface these both, the error has become low, and then the distraction is very less. So this shows thus the low-pass digital Butterworth filter, the speed is always valid.
Comparison between Butterworth filter and Chebyshev filter. The transition band of the Butterworth filter is more when compared to the Chebyshev filter. The number of poles in Butterworth filter is high when compared to the Chebyshev filter. The order of the poles Butterworth filter is more when compared to the Chebyshev filter. The location of the poles in Butterworth filter lies in circle, whereas the Chebyshev filter, the location of the poles lies in ellipse.
Given data, we have to draw the graph. Then from the graph, we have to find lambda and epsilon. Then we have to proceed the steps involved in design the Butterworth filter. That is, first one is find the order of n. Then we find the omega c, that is cutoff frequency. Then we have to find the transfer function of h of s.
The question is that the order is directly given in the question, that is 6th order Butterworth filter or 3rd order Butterworth filter is directly given. So we know from the question we know that n is equal to 6 or n is equal to 3 according to the question. And then to proceed, sometimes the data given is omega c is 1 radian per second, that is the cutoff frequency is also directly given in the question. So we have to proceed the sum according to that, and the transfer function at the last step h of s, to find h of s, we have to just substitute s turns to s by omega c, which is given in the question.
Problem, the order of the filter and order of the sum and omega c is given. In omega c it is in hertz. We want to change it into radian per second. By using n and omega c, we want to find h of s. After that, bilinear transformation finding for h of z, we did h of s. By using Butterworth cutter, we want to find h of s. Sampling rate is given as 8000. In bilinear transformation, we need time. For finding time, f is equal to 120. By using the formula, we want to find d.
About the Butterworth filter, from the given data, you have to analyze Ws and Wp is nothing but omega s and omega p, and Ap and Ap is nothing but alpha p and alpha s. Then you have to find the order of the filter, cutoff frequency, then h of s. In